This is the first limiting reactant problem in the little sheet. So I'll go through that. I'll give you the answer to the second one, but I will not do work on that one. So here's your balanced equation, 3 to 1 to 2. Notice it's giving you pressure, volume, and temperature for both of these. So more than likely it's a limiting reactant then. One thing's going to run out, there's going to be excess. Notice they're collecting the product at a different temperature and pressure. Actually, they're going to collect everything that's left over after the reaction at a different temperature and pressure. So remember, this is a reaction, so one of these is going to be completely gone, your limiting reactant. There's going to be a little bit of one of these left, and you're going to have some of this. Okay, so to get the total pressure at the end, we're going to have to know how many moles of this and how many moles of the excess are there. Plug those into PV equals nRT. So first thing I would do is PV nRT this, and get moles of each one. Okay, I'm not going to show you that work. You guys can hopefully do that, but here's what I got for moles. For moles of hydrogen, I got 2.81 moles. That's how many are available, remember, not how many necessarily reacted. And I got 1.60 moles of nitrogen. So if you notice here, hydrogen has to be 3 times bigger than nitrogen. Well, this number is not 3 times bigger than that number. Okay, and it's supposed to be. So this is your limiting, that is your excess. So I know at the end of the reaction, hydrogen is going to be causing no pressure. Okay, it's the thing that's going to run out first. Some of the nitrogen will be causing pressure. So our partial pressures will be of this and this to make up the total pressure. So knowing that, let's figure out how many moles of this were produced. That'd be normal stoichiometry. So this is our limiting, so we'll start with that. We'll start with the excess. So if I say you have 2.81 moles of hydrogen that we know are used in the reaction, it's a 3 to 2 ratio. Every 3 moles of hydrogen, there's 2 moles of NH3. So if we do that, we get 1.87 moles of NH3. So notice there's going to be that many moles of NH3 produced. So at the end of the reaction, that's going to be causing some pressure. We're going to want to know that. Now we need to get our excess. So start with our limiting, go to the thing in excess. So 2.81 moles of hydrogen we know were used. It's a 3 to 1 ratio. For every 3 moles of hydrogen, there's 1 mole of nitrogen. So 2.81 divided by 3 is 0.933 moles of nitrogen. Remember, that's how much is used, not how much is left over. That's how much is used out of the 1.6 moles that were available. Again, we didn't use all of it because we ran out of hydrogen. So we need to take 1.6 minus that, figure out how much nitrogen is left over. And you get 0.665 moles of nitrogen. So at the end of the reaction, we have those moles. Okay. The total moles there, if we add those two together, is 2.53 moles of gas. So those two together is 2.53 moles of gas. So to get the total pressure, well, we have V, we have T, we're trying to find P, and we know N would be 2.53. The pressure is being caused by those gases. So plugging this into PV equals nRT and solving for pressure, I get a pressure of 3.26 atmospheres. That would be the total pressure. Some of that pressure is being caused by ammonia, some of it's being caused by nitrogen, none of it's being caused by hydrogen. So the partial pressure of each gas, well, for hydrogen to be 0. Ammonia is going to be causing more pressure because there's more moles of it. So I'm going to get the mole fraction of ammonia. So the mole fraction of ammonia is 1.87 moles of ammonia divided by the total moles, 2.53. And that mole fraction is approximately, oops, I didn't even have that on here. I've not done that, I guess, but once we get that mole fraction, I guess we can just do this. We can take that times the total pressure. And that would tell us the pressure of just ammonia. And then 3.26 minus that answer would tell us the pressure of oxygen, or excuse me, of nitrogen. So I got a pressure of ammonia of about 2.40. And the pressure of nitrogen, 3.26 minus that, would be about 0.66 atmospheres. Right? 0.86. Sorry. So pretty difficult problem, okay, but still follows the same principles as other limiting reactant problems.